No, I'm finishing.
Finish your PhD with Vlad Kuregar, and he's going to talk about. Last time was some local invariables for fermions.
Yes.
And I don't know whether it's related to it, but
A bit, yes.
Yes. Okay. So welcome. Thanks.
Thank you very much. So, thanks for the introduction. Thanks for the invitation. So yeah, I'm ANICET TIBAU VIDAL. I'm in the group of Blatko in Oxford, and I'll be presenting the work that we have been doing during the last year with my collaborator, Lucía Vilches-Estevez. And the goal of the seminar was to give a recap of all the results that we have found within Anyonic information theory, but also, like, in order to make this exchange productive, I've tried to link some of the concepts and structures that we find in this type of information with particular aspects of quantum foundations that in here you work on, especially in quantum reference frames. I have to put a very strong disclaimer. I'm not an expert on quantum reference frames, so maybe some of the connections that I will be stating will not be clear, will not work, but this is just to engage in discussion. And I will try to provide a different perspective on constrained quantum systems, which I think may help in thinking about some natural structures or not that appear in these types of systems. Okay, so first of all, what is anyons? Basically, maybe I don't think that people who work on foundations are very used on knowing the theory of anyons, and I want to motivate a bit why this theory is relevant. So the role of quantum foundations is to really study and provide insight in theoretical models that theoretical physicists use to calculate and provide different models so experimentalists can test. So anyons are a model, a working model, that the theoretical physicists in condensed matter physics have come up to describe some phenomenon that appears in physics. It is thought that they provide an explanation to the fractional quantum Hall effect, and Kitaev thinks they would be an ideal candidate to build a quantum computer because he thinks that you have a topological insulation to decoherence. So intrinsically, it is thought that anyons cannot decohere. So you can encode your quantum information in these systems, and then it will be decoherence free. This is why this is why I think it's very interesting that people from foundations that we are used to relate a lot of our concepts to quantum information, we understand these systems, and also it provides a landscape where we run away from our usual notion of quantum mechanics, where it's tensor product based, because anyons have some challenges. The first one is this one, is that there is no tensor product structure. So a lot of the concepts revolved in quantum information are based on the fact that we define subsystems in terms of this tensor product. So the fact that this fundamental system or theory has a complete formulation that does not rely on this structure, it's very interesting from the foundation's point of view, because now we want to understand, like, all of the concepts that we have developed for the last 20 years, or our fundamental knowledge, how does translate for this particular system. Also, creation operations are unknown, because somebody could say, okay, but for example, fermions do not have a tensor product structure per se, like it has a tensor-like structure, but given by the creation operators. But the creation operators in this theory were unknown. This is one of the main contributions that we did with Lucía, was to find the notion of creation operation in this context, so we can start to have an insight from the traditional foundations point of view. And also, like, another challenge which makes it relevant for foundations is that they are constrained by superselection rules. They are constrained by another operation as well. But my particular interest in the topic is that my PhD revolves on superselected systems, especially like indistinguishable particle systems, and this was just a natural avenue to explore. Okay, So the structure of the talk will be the following. First, I'll present what anions are, what the notions of subsystems in anions is, how you can understand them as constrained systems. Then I will provide a very sketchy link and open questions that I would like to discuss with whoever wants here. And then I will focus on some information aspects of the theory, on how to quantify entanglement, what subtleties we have there. Okay, so since this is a new formalism, I think, for most people, I think it's much better that you interrupt me if there's any doubt at this first stage, because otherwise, like, I will be using this formalism all of the time. So if you get lost here, maybe, like, I don't want you to lose you for the whole talk. Okay, so you're seeing the screen, and you're seeing a lot of pictures. Okay, and you may be thinking, how is this quantum theory? Okay, but it is, because so the first thing that it has to say is that anions are represented diagrammatically, and that anions are theory that circumvents the spin statistics theorem, because these are particles that live in two-dimensional systems. So these particles can only exist in 2D, they cannot exist in 3D. And the name anion, basically, it comes because if you exchange two of these particles, like in distinguishable particles, either you get a +1 or a -1, so bosons or fermions, but here you can get any phase. That's why they are called anions, basically. Okay? So let me go into the structure of the theory. So what I want you to have in your mind is that we'll have a 2D surface, and you can put different particle types on top of this surface. Okay? And what is very relevant, the rules that determine the theory, is how these different particle types can fuse. In the sense of, if you have this notion of spin combination, it's a bit like that. In the sense that you will have one particle type, let's say spin 1/2, you will have another particle type, spin 1/2. You can combine them, and you can measure like total spin of the two. You can treat it as a single particle, right? So for spin 1/2, you can have spin 1 or spin 0. So you can have these two different fusions of spin. Okay? So this is the intuition behind this, but in a much more general way. So these are called fusion rules. Okay? So basically, you have to imagine that this is a two-dimensional surface. You have single anion here of type C, and here, and this we call it splitting, because it splits this anion into two anions. Okay? And this is just fusion, because you have two, and it has fused to one. Okay? So, but these rules, this combination properties, we call them fusion rules. Okay? And they are the first level of structure in the theory, because the theory consists of a list of different particle types that you can have and how you can combine them together. Okay? So some combinations are forbidden. Okay? So then your kets, your states, are just the specification of which anion types you have currently, and how do they fuse together if you just encapsulate all of them. This is the idea. So what this diagram is representing is that you have a configuration of A1, A2, AN anions, so just like in the picture, it would be 9. But you have to specify how they combine together. Okay? So anions is a theory very beloved by topologists. Okay? Because
sorry, can I ask something? Like,
yes.
if I have a lower, like if I have all indices that you wrote down,
Yes.
is there a unique diagram that connects? Like I see here fusion, it's very typical. Like I fuse first for A1 and A2 and
Yes.
-1, 2, and so on and so on. But is there any other way?
Yes.
Yeah.
Okay. I will repeat it for the audience. No worries. So Czaslaw asked if this combination is unique. Yeah. So if this specification of this configuration is unique, right? If I understood correctly the question. The answer is yes, in the sense of specifying this, you are specifying the state concretely. However, you could specify the same state in a different way. You could choose a different basis, a different combination basis. So instead of combining like an minus 1 with an, and then combining this one with this one, you could start combining a1 with a2, and then combine it the other way around. And the theory provides you the way to translate between these two bases, okay? But since this is not very relevant for the discussion I want to have, that's why I didn't include it that much. But it's a very good question. Okay, so I was saying that anyons, it's a theory very beloved by topologists because you have these combination rules, okay? And then you can start to do manipulations in the sense of if you have these two together, right, and you move this particle around here, there's a way that the theory tells you, like the modified diagram, how it does change, okay? So it's just this to have in mind. The move that is very relevant, okay, is that it will be a bit relevant for us, is the braiding, okay? Braiding, it's like, imagine that you wake up in the morning, okay, and you want to raise like your blinds and you have like your cord, right? So when you flip the cord of the blind, basically you are braiding, but you can braid in one direction or in the other direction. And the fact of braiding is that if you braid twice in the same direction, you are not on the same state as you were before, basically. So here you can get these phases which do not need to be plus or minus 1. So now we have braided in this direction, right? If we braid again, we will not get a plus 1, which is what we would get with fermions or bosons, okay? Yeah.
Is R, is it one number, or is there like summation?
Yes. No, it's just one number.
Oh, okay.
Yeah, it's just a phase,
Okay.
to be honest. Yeah. Okay, so there are many anion families, okay? But for sake of simplicity, we'll take the simplest one, which are called Fibonacci anions, which basically the fusion rules are the following. We have only two particle types. We have the identity. You can imagine that as being there's no particle there, but you can consider it to be a particle type. Or you have a tau particle, which is the only relevant particle you have, okay? So the identity is such that when you fuse something, when you combine something with the identity, when you fuse it, it has to give you that something. So that's why it's called the identity, basically. It's a trivial thing. Like if I have one anion here and I have nothing here and I combine them, it makes sense that I still have the thing I had before, right? But for tau, it's different. Because for tau, it's like spin 1/2. It's like spin 1/2 in the sense that if I have two tau particles, there's two possibilities that they can fuse. Like they can annihilate each other, so I will get the identity, or I can get another tau particle, okay? And you will see that with this very simple rule, it will give you a lot of unexpected structure that I think it's quite striking the first time you see it. And it's interesting to analyze in foundations. I hope I have given a good account of what this is. Feel free to ask any other question if something is not clear. Moving on. Okay. All right. So in order to provide a more concrete explanation of how these are kets and how you can think of them, I will just work on this very simple scenario that we will have two anions, okay, two Fibonacci anions, and I will describe the whole state space, okay? So the whole state space is just all the fusion rules that you can do. So you can start with the identity, and then it splits into identities. You can start with identity, and it splits with two taus. You can start with one tau, and then it goes to the right. You can start with one tau, it goes to the left, or you can have a tau that splits into others. But there's nothing else. This is just everything you can do, okay? A very relevant point is that anions are super selected by fiat. So directly there's no kinematical formulation that then you super select in anyons. Directly you have a super selection rule within these diagrams. And the super selection rule, it's very physically sensible, which is that the total charge, let's say, these sometimes are called charges, not particle types. So the total charge of the system has to be conserved, basically. Like, therefore, in this 5-dimensional state space that we have here, you have these two super-selected sectors, one with dimension 2 and one with dimension 3. The one of dimension 3 corresponds to this global charge tau, and the one of dimension 2 corresponds to the global charge identity. Okay, I hope this makes sense so far.
Okay, so I got a question to ask.
Okay.
So if these are the processes in which there is are these 5 processes the process in which this is conserved? Because you have tau and then tau.
Yes.
Two tau and
Yeah.
like that.
So Chaslav asked if these are processes, and if these are the processes in which charge is conserved, right? This is what you asked. These diagrams, you don't have to understand them as processes. You have to understand them as states. In order to completely determine the configuration of your space, you have to think of what would happen if you were to merge these two quantities together. So, yeah, so it's better that you think of them not as processes, but as states. And all I'm saying is that all the allowed states are these ones. However, you are not free to do any superpositions between these states, because you cannot superpose states with different charge. Okay, hope it makes sense. Perfect. Yeah.
And so does that mean that in the first sector the charge is like 0 because it's E, and then in the second sector it's something like 1 because you have 1 tau, and then you can't superpose E with T?
Yeah. So Anne-Catherine asked if this means that in the first sector you could think that the charge is 0 because you have, how it's called, because you have total charge E, and in the second sector you have like something like charge 1 because your total charge is associated to the particle tau, and that is exactly correct. And you cannot superpose states with total charge 0 with states with total charge 1. That's the idea. Okay.
I have one question again related to this.
Yep.
On the previous slide, you said that T cross E is equal to the superposition of E plus.
Okay, yeah. Sorry.
But in this case, it would be the superposition of the second diagram and the last diagram.
Okay. Sorry. So in the first, what's your name, sir?
Doesn't matter.
Okay. There's somebody in the audience. There's somebody in the audience, like I'm just for the online thing. Somebody in the audience said that in this slide, here on the bottom left, I said that the fusion with tau is like a superposition between E and tau. However, this is not what this diagram is encapsulating. You don't have to understand this as a superposition. It's just how this fusion, like these different possibilities, are encapsulated. You have to understand this plus as an OR, and this times as what happens if you fuse them, basically. That's the idea. So, and this is expressed in the fact that, so for example, we had now that when you fuse two taus, you can get E or tau. This is how you read this equation. And this is encapsulated in the fact that here, if you fuse two taus, right, you can have E, but you can also have the other possibility, which is tau. This is what, exactly. But it has nothing to do with superposition or the coherence.
It's just fine. It somehow appears to be somehow connected, but the matrix precludes this kind of, okay, whatever. Yeah.
Yeah, it's okay. But yeah, so the super selection rule is just you have these two different sectors, you cannot have coherence between them. That's it. So, but to give further intuition, like you could look at this diagram and naively think, oh, but in the left, I have either E or tau, so you could think this as either 0 or 1, right? In the right, the same, and in the bottom, the same. So you could think this as a 3-qubit system, basically, where you codify E as being 0 and tau as being 1, and you could try to have this kinematical space where you have a tensor product, and then think of this theory embedded there, right? This would be the constraint that you will have to apply, okay? And this will be the constraint you will have to apply to restrict the 8th-dimensional 3-qubit system to the 5-dimensional qubit system. You'll have to apply further constraints to incorporate the superselection rule, but I was a bit lazy and I didn't want to put it in the slide. But this is just to show how these anyons are naturally constrained systems in this very nice language, nice diagrammatical language, okay? You can see that with these sectors, you clearly do not have a tensor product between the anion on the left and the anion on the right. Because the anion on the left can be 0 or tau, the anion on the right can be 0 or tau, but however, you have 5 possibilities on the global space. You have one extra that what you would get if you would think that these are just 2 qubits that you tensor product between them. And if you think that these are 8 qubits, then you have to restrict your space even further. So you do not have a natural tensor product to define the left subsystem and the right subsystem that you would naturally associate with your lattice if you partition your 2D space in two. Okay. I hope I got most of you. And yeah. So let's talk about subsystems. How do we define them? How can we define subsystems in this very weird thing? Because we have this very strong intuition that I have a 2D space. I have some anyons living on the left, have some anyons living on the right. I should be able to partition this in two and talk about the correlations between the left of my lattice and the right of my lattice. So how do I do it if I don't have a tensor product? That's the question. So first of all, there's a lot of subtleties with onions. The first thing is that this partition in these lattices, in these regions of the manifold, let's say, they depend on how do you connect the regions. So what I mean, for example, we have these regions, right? We have region 1, 2, 3, and 4, okay? And now we want to do the bipartition between 1 and 4 and 2 and 3, okay? So what you do, okay, how do you get from there to here, okay? And what, this is the natural basis for this decomposition. What you do is 2 and 3, you link them together, right? 1 and 4, you link them together from behind, and then you project on the left. I don't know if this is very clear. Maybe not. Can somebody say if yes?
This way you, if I understood, you construct a state.
You construct a preferred basis for...
Yeah, multiple liberalization of the states, but that's one decomposition, prefer decomposition in some cases.
Exactly.
Which you would say, like, which somehow make these subsystems more clear.
Yes, exactly. However, what is unusual about anions is that the way you link these two matters. So you could have the same regions with different subsystem decompositions. Because you see, when I link 1 and 4, I make it go behind 2 and 3. That is why like this goes behind it. But I could go connect 1 and 4 not from behind, but like from in front, and then it would go in front. And by that beautiful question that Czeslaw asked in the first slide, this would correspond to a different basis. So you would have, and they are not equivalent at all. So you would have different notion of subsystem depending on how you connect these spaces, okay? I would like to link this to subsystem relativity at some point, but the speculative part will come shortly. But so far, you could just, this is not speculative, like you could just fix a preferred basis. So for example, this is a very clear one, right? Like I have 1, 2, 3, and 4. And now you connect 1 and 2, you connect 3 and 4, and you just project them to the left. And that's why you have this preferred basis. So now, like, if you want to study correlations between, between this, like between the bipartition 1, 2 with 3, 4, you should express all your states in this preferred basis, and then you can do some things with that I will go now.
So again, for a stupid question, when you say project on the left, in this particular case, you mean projecting 1, 1, 2?
No, yeah. What I mean is like to obtain the diagram, like to obtain this planar diagram. So I'm sorry, like I do not reach, but my point is like the way I imagine this is like you will connect 1 and 2,
Yes.
you will connect 3 and 4,
Yes.
but this lives in 3D, and I want to make a planar diagram. Therefore, like you get like all these dangling things, and you project them on the left, and when you see the projection, it looks like this.
What defines left and right? Like, what does it mean that you project?
Oh no, yes. No, this is just on the picture. I mean, like, sorry, yeah. You could do it in a different way. That's the whole point. That you could choose a different basis that is also natural, but it would, like your notion of subsystem is not only like the two regions that you are gluing, it's like in the order in which you are gluing them and where you are moving them in front or on the back. It's what determines your notion of subsystem. Because your notion of subsystem is intrinsically associated with this notion of preferred basis.
Okay.
I hope it makes sense. Okay. All right. I don't know how I'm doing on time, by the way. I didn't practice the talk, so.
We don't know how many slides you have. But
Okay.
I'm leaving on 22nd of January.
Well, that's good. Okay. Sorry. Yeah, what I want to say. Yes. So once you have this notion of this intrinsic bipartition, this notion of subsystem as a preferred basis, you can define the notion of local unitary and local observable. Okay? Which is, for example, here if we have n anions, a local unitary that acts only in the 2n of them, when I will go to here. So this diagram, maybe you are wondering what it is. I just put a ket here and a bra here. That is why it's an operator. And they are joined because of the superselection rule. Because they have to be the same space. I hope it makes sense. So like if I cut it, right, you could see that this is a ket, right? You could see that this is a bra, right? But I can glue them because the superselection rule tells me that my ket and my bra have to have the same global charge. That's why like they are continuous, okay? So this is how you represent observables and unitary, like basically operators that preserve the sector, okay? By putting a ket and a bra and just gluing them together because you can, because this is the same. So going back to local unitaries, a local unitary has to leave the first anion invariant, of course, has to leave the global charge invariant as well. But you could change anything about the other ones. But it's important that you have this in this preferred basis, right? Because so the partition between this is that you have A1 and you have the rest of the thing. So it's intrinsically associated to the preferred basis, which from now on we will just use like this one. But you could have other ones in the physical setting. Hope it makes sense. Did I lose somebody?
On the left-hand side, I see immediately that one is not touched, that is identity.
Yes.
Here, I mean, you put primes and non-primes, and then
Yes.
it indicates. But how would I, without having your help of putting primes on some lower row,
Yeah.
knew that A1 is unchanged and all others are changed? Is this in the diagram?
Yeah, it's not necessary that these are changed, because of course you can have a local unitary that is just like the identity, but the possibility is just this.
But how do I know that there is a possibility that those will be changed, while there is no possibility that A1 will be changed?
Because this is the same.
I mean, you put it the same.
Yes.
Index. Is there anything else which in diagram itself tells you whether it will be changed or not?
No, just that the
Because here on the left-hand side, you don't need to put me one. I mean, you need to tell me which is which dimension
Yes. Okay.
You can put 2 and 2 in the same,
Yes.
and I still know that they could be changed.
Okay, I understand. That is a very good question. So here, it's not this 1, 2 labels the lattice sites. It does not label the particle type in that lattice site. So this could have like this A2 prime, and here you have A2, you know. And another insight that I want to give is like, you can think of this as like, okay, forget about this picture. This is maybe more comprehensive, but I told you I had some cats, right? From those cats, you can do all the operators. I told you that there's a super selection rule. Therefore, like these operators, you need to preserve like the sector. So a general unitary, it would be just a sum of these diagrams where like you can change all the labels here, all the labels here. Meanwhile, like this is just unique. Like this would be a general unitary on my n anion space, right? Now the question is like, what is the constraint on this general unitary, on this sum, such that my unitary is local on the 2 to n anion sites? And the answer is that all the contributions where, like all of the diagrams where this index is different from these indices, like it has to have contribution 0, like the weight is 0. This is the way I think about it. I don't know if that makes sense. Yeah? No?
Okay. I think we should go.
Okay, sorry. Yeah. The idea is just that you have a notion of local unitary, and what the local unitary does, expressed on this diagrammatic form, is that it leaves invariant the particle type in which it does not act. Meanwhile, it may change or may not change the other factors. And you see that all the interactions that A1 has remain unchanged, because A1 interacts with like A1 only informs on the global charge here, and the global charge it's preserved as well. Yeah?
Maybe to clarify, could I have a different shape in terms of fusion and still have A1 and A1 be the same?
Yes.
Top and bottom? And
Yes.
still represent?
No.
No. So
Sorry.
So my question is, does A1 have to neighbor just A2 and to fuse just with A2, or could I have?
So you have to have this preferred basis to express this local unitary. You could have a different basis where this A2, instead of going there, it fuses here, right? And the fact that A1 is preserved will not be enough to say that this is a local unitary.
So that there is something in the diagram itself without your labels.
Yes.
Huh?
Yes, that's true. Yeah, that's true. There's something in the diagram which is the fact that you choose this preferred basis where when you do the bipartition between the local part and the rest.
It interacts or collides only with the charge.
Exactly. It's only in the diagram. Exactly. Not only on the indices. I hope it makes sense.
So if there were several nodes that wouldn't have a unitary actual level, they would all have to individually connect to this thing in the middle.
Yeah, exactly. So for example, if you want some local unitary that acts on 2, then what you would have to do is like these 2 should be detached. This 1 should reconnect either from below or from in front, and then like connect with 2. This is the idea. Does it make sense? Okay. So the thing is like once you have local observables and local unitaries, you have a notion of subsystem. This is very well expressed in this paper by Kiribella, but it is enough because if it satisfies some condition, which is an embedding condition that these local unitaries and local observables, it's easy to map them to the reduced space of n-1 anions, so that there's a mapping, a faithful mapping between the two. But here you have it thanks to the super selection rule. I hope it's something. Okay? So now, once you have this, I will explain the story. So last year I came here and I told you that there's some there's some local realistic interpretation possible in fermionic systems and in qubit systems by using creation operators. That if you have creation operators, you can have a local realistic interpretation. So my goal on entering anyons was to understand these local hidden variables, as Czeslaw calls them, in anyons. However, my natural choice, which was creation operators, because it was natural for bosons, for fermions, and for qubits, creation operators serve that role, was not in the theory. So then I wondered if still that local structure was there. So I saw that yes, that local structure is there, and thanks to knowing that that local structure is there, I could guess what the annihilation operators in anyons were. So this is what I did. I don't know how we are doing on time. I don't know how interested you are on the specific way I found this, but what we did with Lucia was to use this insight from foundations to define creation operators in anyons. The insight for Fibonacci is that even though you have a single particle type, since you have two possibilities on how to fuse two different tau particles, you actually need two creation operators, even though there's a single particle type. Okay? So in a single site, you need two creation operators to describe Fibonacci anyons. This is very interesting for people in condensed matter because now that they will have creation operators for simulations, it's very easy. There's a lot of methods done in terms of creation operators. Also, like you could think you could think of Hamiltonians. You could build like Hubbard-like Hamiltonians using these creation operators. You could study their properties. You could see the commutation relations, how weird they are, etc., and it provides a lot of insight on different possibilities of different algebras that you could consider to represent quantum systems, more than like just the usual commutation relations, like for commutator or anti-commutator. Like what are the other possibilities that you can have? We can talk more about this, but for sake of time and to get to the more speculative part, I would skip exactly how I define them. Maybe like all I want to say is like they look just like, of course they are not observables. That is why like now we have like the discontinuity between the ket and the bra that I was mentioning before. And if you express fermionic systems in this diagrammatic form, the way we obtain these annihilation operators, we would obtain exactly the same fermionic annihilation operators. And this phase, it's just the minus sign. It would be the minus sign in the fermionic annihilation operator that you usually have. That's it. But yeah, if there's some request to explain this, later I'll do it.
And then you would have only one, like it will collapse.
Yeah, exactly. Yeah, because for fermions, okay, for fermions, fermions always, in order to define fermions here, they always annihilate. It's not that you can bring two fermions and the total charge is still fermionic. Like it will always be bosonic. So then like you don't need like the second one. That's the idea. Okay. So yeah, what I was mentioning, that my PhD revolves about this interpretation of quantum mechanics. Last year I came here, I gave a talk about how fermionic annihilation operators can be interpreted as local elements of reality, in the sense of that if you use the Heisenberg picture, you fix an initial state, you evolve the creation operators. There's enough information on the evolution of each creation operator to retrieve all the information about the global system. So in this sense, it's local realistic. Now that we have creation operators for anyons, even though it's beloved by topologists, and they like to say that anyons only depend on global properties of the manifold, etc., there's a way to also recover a local realistic picture using these creation operators that we have found with Lucia. So here comes the speculative part. Okay. So one topic that maybe it would be interesting to discuss, that it has been since I'm not an expert in quantum reference frames, I'm very confused by them. And since I'm very used of working with this interpretation of quantum mechanics where everything is local and you work on phase space, I wonder what is the role of the initial state and the initial descriptors that you use, like the initial value of the creation operators that you use. If you could interpret them somehow as some external reference in this operator valued phase space. This is just something I dropped there. And how then does this relate with internal quantum reference frames, which is what I think you do, how these two things translate to each other. Okay, so now, quantum reference, like the speculative part. Quantum reference frames. So this constrained system, I think, what it provides, it's just a more physical perspective on what constrained systems and gauges give, because you can think about the bipartitions, you can think in this particle way about these combinations and recombinations of objects. So it provides a different point of view, like less algebraic, and maybe it provides more physical, a more physical understanding. At least I want to believe so. Yes. So, but also it provides an avenue, like a toy model, to test what is expected in constrained systems, like what structures are there. Like, for example, the fact that you do not have a tensor product, but you can still talk about like local unitaries, local observables, and now you can have creation operators, even though you do not have like a tensor product structure. And now we will see that we can even go to entanglement characterization, correlation characterization between subsystems, even though you do not have a tensor product structure. Wonders that for people who work on constrained systems, sometimes they find this, that some space that you get like does not decompose on a tensor product, and then they think, oh, that doesn't, then it means that I do not have a coherent subsystem understanding of this space, for example. Also, like other structures that are expected or not expected. So all these arrows are just speculative points that if some of you is interested in discussing or exploring, I would be very interested in doing so to learn more about what you guys do also. So, for example, when you study the constraint that constrains like the 3-qubit mapping to the 2-anion system, you see that is a term that it has like interactions. Like, so if you think like in the Hamiltonian formalism and in Page-Wooter setting, this would mean like that the clocks are interacting with the system. So this wonders that if instead of having like this system, you have a Hamiltonian system where you have interacting clocks, if some of the peculiarities and the properties that we have found here in anions will also be present there. I would expect so. So if sometime I'm working on this other formalism and I found that structure, I hope to not be that surprised, because I know that in this model that condensed matter people use, you have the same structure. So I would expect so. Also in subsystem relativity, in this paper by Amat and a bunch of people, how it does translate this choosing these partitions of your lattice space with subsystem relativity. And if subsystem relativity is even a thing, because there's a lot of emphasis, at least in this paper, if I remember correctly, on having like a tensor product. So how you could, if you could define like in a consistent way what local observables are a priori, and then see if you still have this relativity in that case. That is one speculative area where we could go. Yes, also like this, when you study anions, right? There's a huge debate in in identical particle systems and information or foundations between the particle picture and the mode picture. What is more fundamental? What is more convenient? what is more fundamental. So when we consider the subsystem for anyons, right, we are not tracking the difference between the particles. We are tracking the difference between the notion of subsystem is mode, because we are talking about left and right. We're not talking about tau or no tau, basically. However, when you have the 3-qubit mapping, when we are tracing out left and right, we are tracing out a qubit. So we are tracing out a full particle. So in the works I've seen on quantum reference frames, usually you have this first quantized approach where you have some kinematical space, and what you refer as tracing out, you trace out like a whole particle. You do not have like this second quantized view that maybe it would be advantageous for you to explore. Maybe you are already doing that. I don't know. I thought it was just some connection. Yes. So the last thing I want to talk, because even though like I think a lot of people here do foundations, I think most people here also come from like a quantum information perspective, or at least they are informed by quantum information. They think it's a good tool to have. There's also people from theoretical physics. Okay, sorry, but at least I come from quantum information perspective, and when studying this, once you have like these subsystems, I want to study how to characterize entanglement, how to characterize correlations between these subsystems, okay? And you found very particular things that if I have time, I will talk about them now, because this is some work that we are doing. This is very much work in progress that we are developing, and I think it's very unexpected the first time you see it. So I don't know if I have time, to be honest. Yes, I do? Okay. But yeah, so feel free like to talk to me about any of these topics or anything else that you have thought about, or if you see any connection with this beautiful theory. Okay. So in these non-abelian anyonic systems, you have these particularities. So you have pure states. We define pure states as usual. And in these pure states, we want to quantify entanglement. The usual way to quantify entanglement in pure states is just the von Neumann entropy, right? You could do, why can you use the von Neumann entropy? Usually it's because you have a Schmidt decomposition, okay? And what the Schmidt decomposition guarantees you is that the spectra of the two marginals in a bipartite system will be the same, okay? Then you can use the von Neumann entropy in either of the marginals, and since it's the same spectra, it will give you the same result, and it will quantify how much entanglement you have, okay? However, in anyons, you cannot do this. Why you cannot do this? Because it's not true. It's not, since you don't, like first you don't have a tensor product, okay, but you could still think maybe I have an analogous Schmidt decomposition, but no, you cannot have it, because you can find, like most states, to be honest, will be of this form. It will be states that they are pure, they are bipartite, and you can take the partial trace of A or take the partial trace of B, and they will have completely different marginals, completely different marginal spectra, okay? The extreme case is this one, where we have this state, okay? And if you trace out this part, you have, so if you trace out A, you have a maximally mixed state, okay? Because the anion here can be in the identity or can be in tau. One naively would think, oh, but this, like if you encode it like in a qubit system, right? And like in the 3-qubit case, and you trace out in the 3-qubit scenario, then you get plus state. You don't get identity over 2. However, plus is not allowed by the super selection rule. So in the partial tracing procedure in anyons, you have incorporated the super selection rule, which makes this asymmetry between left and right in this case. So this is a very extreme case because rho B is maximally mixed and rho A is completely pure. Okay, so then when you calculate the von Neumann entropy for B, the entropy is just 1, and for A is just 0. So now I want you to guess. Like this will be interactive. I want you to guess. Do you think this state is entangled or not?
How do you define entanglement?
Uh,
If it doesn't have an empty structure, what does it mean that something is entangled?
Okay, I will go into there. Like, I will tell you for now that there's a way you can do it. You just have to guess if it's entangled or not. You're right. Yeah, this is not an entangled state. Concretely, it's an uncorrelated state. Okay, and the way you can define entanglement is because you can define the notion of uncorrelated. The notion of uncorrelated, it's equivalent to the notion of a product state in how it's called, in pure states. So in pure states, uncorrelated and product state, when you have a tensor product, they are equivalent. So here, we don't have a product, but we have still the elements that appear in the equation to define uncorrelated states. So you can put the equations because you have local observables. You have all the local physical observables. I forgot to say that this is for all OA, OB. This is what rho has to satisfy in order to be considered an uncorrelated state. And we have been able to find all uncorrelated states in this two Fibonacci anion case, which they look like this. Okay? So basically, these are states that cannot have at the same time a non-trivial contribution between a tau being on the left and a tau being on the right. Okay, these two. Okay, but all of these states are uncorrelated. So there's there's a lot of states.
Sorry, how
Yes.
do you define rho A and rho B
There is just the object that lives in a single anion state space, such that trace of OA rho A is equal to trace of OA rho. So you have an OA embedded in like in the bigger space, in the two anion space, but this OA you can also express it in the single anion states.
such that
Yes.
this is equal, right?
Exactly. Yes. Okay. So, yeah. So you have this very weird structure where you have uneven marginals, right? So somehow, like, Alice and Bob do not share the information equally, or this is what you would think, but this state was a very bad example of it because there's no correlation. They are just completely uncorrelated. Okay. More interesting stuff, which will, and going back a bit to the speculation. Sorry. Usually, you have product states, right? And the way, like most tasks, so for example, like the resources that you use in order to quantify entanglement or use entanglement as a resource, it's local operations, because local operations are free in the sense of that they do not increase entanglement, right? However, it's not only that they are free, it's like that they are super free. Not that they are super free, but they are the only operations that are free, that they do not increase entanglement in any state when you apply them, right? Because you can map any, in the sense of, you can map any uncorrelated state to any other uncorrelated state in pure states, so product states, by using only local operations. So that is why they are very important in usual quantum information theory. However, here, local operations are not enough. Local operations are very weak. So if you apply a local operation to this sector, to a state like this, at most, I think it was that you can swap between these two. You can swap these two indices. But like you cannot change the value of these weights. You cannot go from this type of state to this type of state by applying local unitaries. You cannot do anything like that because local unitaries are very restricted by the superselection rule. So now we have a structure that is kind of similar, or at least maybe I think they are, to the structure of alignable states in quantum reference frame, in the sense of that you have alignable states, and the way to map between alignable states, it's not like you can do it in a unitary way, but that unitary, if you apply it to another alignable state, maybe it does not get you to a desired alignable state. So it has to be state dependent. So, okay. That's a very good question. Czeslaw asked if what are alignable states. I think alignable states are the states, I think some reference I saw, are the states in which you define like a reference, that they are like picked in the reference, and then you have tensor product, like the state of the rest of the system.
It's any state where the reference frame is in 0 or E, like the previous state. Any state that we use. It's like the state in a reference frame, where the reference system is in guard.
Yeah, so Anne-Catherine said that there are states in a reference frame where the reference frame is in E or 0. So I think you have like a similar structure there. So now this is a challenge in the sense of I would like to have a good entanglement measure for anyonic systems that capture this asymmetry. So we are thinking actively of different routes. If you have some suggestions, I would be delighted to listen to them. So one is to use just relative entropy and see what happens. The other is to see it more operationally, in the sense of, okay, I will give you an entangled state, and I will try to measure how useful that entangled state is, in the sense of, can I do teleportation? How faithful can I do teleportation? Could we have the case where you can teleport from A to B, but not from B to A? These are the kind of questions that we would like to explore in order to have a good measurement of entanglement in these weird anyonic systems. Also entanglement distillation in the same lines. But it's very imperative that we understand these transformations between uncorrelated states that generalize local transformations in order to produce this resource theory and also entanglement measures. Okay, so just to finish, I hope that during this talk I introduced you faithfully to what anyonic information theory is, and I hope these are some of the results and connections that I hope we can explore during the next 2 days. So basically, it's just that anyons, I hope they will provide you a different perspective on constrained systems and what is to be expected, what is not to be expected. Second, that I want to remark a bit, this is a bit of promo, just that we have found this creation and annihilation operators for anyons. I think it's a very cool result. Hopefully it will come out soon in paper form. And that you can use them as local elements of reality. We can discuss this interpretation if you want. Then that tensor product decompositions are not necessary to define subsystems and entanglement. It really helps you because you have a much cleaner structure, but in order to define subsystems, they are not necessarily at all. And to define entanglement, we have a definition of entanglement, but it's the measure of entanglement, it's what is more complicated. Then that subsystem relativity is expected in constrained systems, especially in interaction constraints. And the ways like how you deal with it, especially without thinking about the tensor product. Then that this nice finding that pure anyonic states have asymmetric marginal spectra, and that the von Neumann, therefore, the von Neumann entropy is a very bad entanglement measure for pure states in anyons, and that local operations do not cover this state set, and I think it's similar to alignable states in quantum reference frames. Maybe I think this result, it's especially if there are some projects where you try to, when you change reference frame, if you want to quantify how much entanglement versus coherence trade-off you have, this is something very relevant, because it's necessary to have like these mappings to be completely specified, and when you want a good entanglement measure to quantify this entanglement in these kinds of systems. And that's it. Thank you very much. Any questions?
I have a question.
Yeah.
Like anyons and this topological quantum computation has been known for like 20 years now or something.
Yeah.
I'm surprised. So nobody has worked out so far, how it works when you have more anyons, how they interact with each other. Because it seems that all those things you said about there's no tensor structure and so on, that there are like you can define subsystems and then you can study entanglement. I would presume that this is one of the first things that one would do once those anyons are known, like as elementary subsystems. Like if you want to do quantum computation, like one of the advantages as far as I understand is that you have multiple qubits and the state space grows exponentially with the number of qubits, right?
Yep.
So I would expect that one anyon is not enough to do quantum computation. So
No.
I would again guess that people already like some 20 years ago had to figure out what to do if you have many anyons.
Yeah.
In order to do something interesting with that. So and these people would should have already have an idea how different anyons interact with each other, right? And the first thing how entanglement distributes over this system. So I'm so surprised that all of what you presented, all these things still look like open questions.
That's a very good comment. It's true that anion systems have been known for 20 years. However, the insight, they were used directly for topological quantum computation, and they are not used per se. So like they are used to encode quantum information. It's not, they are not that much studied from the quantum information perspective as systems in their own, just as encoding spaces to use their topological properties. So the way topological quantum computation works is you would never use a 2-anion system to do quantum computation. You would use a 3-anion system. And you would not encode your information on the particle types you have on the surface. You would do it on the global charge that you have hidden there. That's why they think it's resilient to the coherence, because it's on the global charge, not on here. So when they study entanglement on between the logical qubit, not on the anion information per se. I hope that makes sense. Yeah, it's surprising. No, yeah, I was surprised as well. I was also surprised to see that there were no like creation operators. That there are some works trying to describe anionic quantum information, I have to say. So for example, here, but their insight is from condensed matter physics. So they make some assumptions that I don't think, well, with my collaborators, we don't think they are correct. So for example, here, they say, for example, that it's not interesting to study these states because the global charge is tau, and they think that in their system there would never be like something with global charge tau, for example. That is one example. But at the same time, when they do their encodings, they use states with global charge tau. So it's a bit inconsistent because it's different people with different aims. So there's also some works trying to characterize information, but they only consider global states where you have charge E, because then they say that this is not a pure state, because they give some, using these diagrammatics, if you use a particular normalization, if you square like the row, like the density operator, if you square it, then it's not, the trace of rho squared, it's not 1, therefore they say it's not pure, but that is if you use a particular normalization that they like to use. So there's several works.
And I guess it would be too obvious to use this semantic
Yeah, exactly. So our insight is more like we want to understand an ionic system from by using all this, all of this space, not the encoding of qubits into anions.
Yeah. So you cannot just translate the well-known notions of entanglement and so on using this mapping into the anyonic.
Exactly, no, because it's not a faithful map.
Okay.
That's the idea. Thanks for the question.
You're welcome.
More questions? Apart from those that this is nothing new.
No, I'm absolutely
No, it's a good question. No, to be honest.